Hello everybody, I hope you're doing well. Welcome back to another video in the calculus playlist. So in the previous video, we have gone over the concept of limits and how we can use it to identify what value a function approaches when x approaches a certain number. So this video is going to go over some properties of limits. Most of them should be intuitive to you, but we're still going to go over them nonetheless. And we've also talked about trigonometric properties of the unit circle in the prior video. So with that being said, let's just jump in since we have a busy agenda today. So today, first off, we're going to cover properties of limits. So what are the properties of limits? Well, here's a couple properties that might be handy. Some might be intuitive, but it's good to jot them down. So if we have the limit as x approaches c of f of x plus g of x, we can essentially break this function of f of x plus g of x into two separate limits as such. So limits are additive, and we can kind of use the addition and subtraction operators to separate limits of individual functions and solve each subproblem individually. Likewise, we can also pull out constants in limits. So if we have the limit as x approaches c of, say, k f of x, where k is a constant, this is simply equal to k multiplied by the limit as x approaches c of f of x. So we can separate via addition subtraction in limits, and we can even pull out constant multipliers. We also have a quotient property of limits as such. The limit as x approaches c of f of x divided by g of x equals the limit as x approaches c of f of x over the limit as x approaches c of g of x. So we see here the constant multiplier rule, the addition of functions rule work for limits, even quotient of functions work. And likewise, we could even do product property of limits too. So if we have the limit as x approaches c of f of x multiplied by g of x, this is just going to be the product of the individual limits. And the last property we've taken care of the individual arithmetic operations here. The last property we have is the composition property rule. So let h of x equal f of g of x. So this is a composition of functions because you have a function inside of another function. So this g of x is nested under an f of x. So if we want to take the limit as x approaches c of h of x, well, this is equivalent to taking the limit as x approaches c of f of g of x. And one cool thing we can do with compositions is that we can bring the limit essentially inside. So this f function is on the outside, but the g function is on the inside. So we can essentially take the limit as x approaches c of g of x and then take f of that limit. So this is going to be equal to f of limit as x approaches c of g of x. And this property can come in handy if f is especially a complicated function you want to evaluate, but g is a very easy function to evaluate. This composition property can come in clutch. So with that being said, these are the properties you really need to know about limits, and the best way to understand these properties is to put them through example problems, which we're going to make the bulk of the video focus on. Okay, so I'm going to change my color to green, and I'm going to move down to the example problems. Keep these properties in mind though, and you'll see them in action with the examples. So there are a lot of ways of solving limits, and the approach you choose depends on what's at hand. So I think the best way to know what approach to choose is going through example problems and kind of like building some intuition as to what might be done. So, okay, with that being said, let's start with problem 1. So we want to take the limit as x approaches 2 of 8 minus 6x plus 12x squared. So we see here clearly that this is a quadratic function and it's continuous in its input, right? So we don't see any discontinuities, right, from the looks of it. And thus, what we can try is one simple approach we can do is plug in, right? So direct substitution. So we can simply plug to it and that should be the answer. So this will be 8 minus 6 times 2 plus 12 times 2 squared. So this will be 8 minus 12 plus 48, which will be negative 4 plus 48, which is 44. So this is just a direct substitution limit example. So number 1 is pretty straightforward. All right, let's go to problem 2. Okay, so at problem 2, we want to take the limit as z approaches 4 of the square root of z minus 2 all divided by z minus 4. So let's try the approach we had in mind initially from problem 1. So if we plugged 4 in, right, the numerator would be square root of 4 minus 2, which is 0, and the denominator would be 4 minus 4, which is 0. So you'll get a 0 over 0 scenario, and that's usually not a good outcome we want to have. So what can we do instead? Well, we can do any operation that keeps the value of the function the same, but like, we don't want to change the value, right? But we can do anything, like anything is fair game when we're solving these limits, as long as you don't change the value of the original function. So what we can do is one common technique if you have like square roots and stuff like that in this form is multiplying by what's called the conjugate. So the conjugate of square root of z minus 2 is square root of z plus 2. And we have to multiply this in both the numerator and the denominator to not change the value. Okay, so what do we get? So this is going to be equal to z minus 4 over z minus 4 times square root of z plus 2. And now we can cancel the z minus 4 here. And if we take the limit as z approaches 4 of 1 over square root of z plus 2, where the square root of z plus 2 is right in the denominator, this is going to evaluate to 1 over 2 plus 2, which is 1/4. So for a problem like this, you want to use the conjugate. That way, like, you're kind of getting rid of this pesky z minus 4. Cool. So hopefully that makes sense to you. We're going to move on to problem number 3. So problem number 3 might be something that might ring a bell to you. So we have here the limit as x approaches negative 5 of x squared minus 25, all divided by the quantity x squared plus 2x minus 15. So if we plug negative 5 in directly, right, you're going to see that you're going to have a 0 over 0 scenario, right, because the numerator will evaluate to 0 and the denominator will also evaluate to 0. So what do we do instead? So in problem 2, we had to multiply by the conjugate to find a common term we can cancel out in both the numerator and the denominator. For this type of problem, we notice off the bat that x squared minus 25 can be written as x minus 5 times x plus 5 by difference squares, right? And if we're going to decompose x squared minus 25 into x minus 5 times x plus 5, we might as well try to decompose the denominator. So x squared plus 2x minus 15 is a factorable polynomial. And if we factor it, right, it's going to be x plus 5 times x minus 3. You can check yourself that this factoring matches up. And we'll see here that x plus 5 is in both the numerator and the denominator, so we can cancel them out. And now we have the limit as x approaches negative 5 of x minus 5 over x minus 3. And thus, this is going to equal, I should be writing the limits in here, by the way. And I should have actually done that in the second problem, but we learn from our mistakes, right? So we're having the limit as x approaches negative 5 of x minus 5 over x minus 3. So this is going to simply equal negative 10 over negative 8, which is equal to 5/4. All right, cool. That makes sense for problem 3. So we've seen in problems 1, 2, and 3, factoring, direct substitution, or multiplying by the conjugate are valuable techniques. Now let's look at problem 4. This is a slightly different function, right? We have f of x, which is defined as a piecewise function. The first piece being 7 minus 4x when x is less than 1. And then the second piece is defined as x squared plus 2, but x is greater than or equal to 1. And we want to find the limit of, as x approaches 1, of f of x. Okay, so what do we do in this piecewise function? Well, we see here that the x equals 1 is kind of the separator of the two pieces, right? Of the 7 minus 4x piece and the x squared plus 2 piece. So I think what we might want to do is evaluate limit as x approaches 1 from the left side of f of x. And we also want to find the limit as x approaches 1 from the right-hand side of f of x. And the limit is set to exist when x approaches 1 when the limit as x approaches 1 from the left-hand side of f of x agrees with the limit as x approaches 1 from the right-hand side of f of x. Now that we have that piece, what is the limit as x approaches 1 from the left-hand side right here of f of x? So the left-hand side is x is less than 1. So the 7 minus 4x piece right here. Well, this is a linear function, so we can simply plug 1 in, right? So this is going to be equal to 7 minus 4 times 1, and that's going to equal 3. What about from the right-hand side? Well, this is going to be x squared plus 2, and x squared plus 2 is a continuous quadratic function. So we can directly substitute 1 in, right? So this is going to be 1 squared plus 2, and this is going to equal to 3. They agree. So the limit definitely does exist, and the answer is 3. So hooray, we got a happy scenario right here for problem 4. Sometimes there might not be such a happy scenario, and we'll see that example later on, but keep this in the back of your head. All right, now comes problem 5. Okay, we want to evaluate the limit as h approaches 0 of 6 plus h quantity squared minus 36, that whole quantity divided by h. All right, so you might think that we might want to multiply by the conjugate right here, but I think if we're looking at this expression for the first time, we see here that the 6 plus h quantity is squared. So maybe it might be a good idea to expand that out, right? So this is going to be equal to the limit as h approaches 0 of 36 plus 12h plus h squared minus 36 all over h. All right, so now what can we do here, right? Well, we can cross out the 36 right here. And we see that we have a 12h plus h squared over h, right? So we see that h is a common factor in both the numerator and denominator. So this is going to be equal to the limit as h approaches 0 of h 12 plus h. So what we're doing is we're kind of factoring this expression by pulling out the common term of h in the numerator, and the denominator is going to be h. And what happens? Voila, the h is crossed out. And now we have the limit as h approaches 0 of 12 plus h. Well, when h approaches 0 in this case, this term here vanishes and the 12 remains. So the answer simply is going to be 12. Now, this limit, by the way, like as a teaser into a future video, this limit in this form is very, very special. And we will delve into what this limit exactly means and how we can decode this. But for the sake of this video, we're kind of focused on solving limits. So keep problem 5 like the form you see in the back of your head because we will see it in a future video. Alrighty, cool, sweet. Let's move on to problem 6. Okay, so we want to find the limit as x approaches 0 of x over 3 minus the square root of x plus 9. Okay, so if we do direct substitution as our first tactic, right, we see that the numerator evaluates to 0, right? But if we look at the denominator, right, you have 3 minus square root of 0 plus 9. So that's 3 minus 3, which is 0. So you get a 0 over 0 form. And that's kind of bad, right? So if you remembered from problem 2, right, we had like, a number minus a square root of something. Maybe we can try, finagling this expression in a way similar to problem 2, such that we don't have this pesky square root that's causing the 0 over 0 scenario. So we can try multiplying by the conjugate again. So this will be 3 plus the square root of x plus 9. And just to make sure you guys recall, the conjugate of this term is simply the same numbers, but this minus changes to a plus, right? So instead of 3 minus square root of x plus 9, it's 3 plus square root of x plus 9. So what does this come out to? So this is going to be the limit as h approaches 0 of x times 3 plus square root of x plus 9. over, we have a difference of squares again coming along. So this will be 9 minus x plus 9. All right, and this is going to be equal to the limit as h approaches 0 of x times quantity 3 plus the square root of x plus 9 over negative x, right? Because the 9's here kind of cancel out, so I'm just kind of simplifying the denominator. And, oh, sorry, this is x, not h, right? Now we see the x's here cross out, right? And this is going to be equal to the limit as, oh, sorry, this is supposed to be an x. Okay, so now we can simply plug x equals 0 into this expression, right? Because we won't have a 0 over 0 or a weird case. So 3 plus the square root of 0 plus 9 is 3 plus 3, which is 6, multiplied by negative 1. This is going to be negative 6. And voila, we've used the conjugate and seen it save the day for problem number 6. Okay, moving on to the next problem. All right, problem number 7 is another piecewise function. And we have here the two pieces, f of z equals 6z when z is less than or equal to negative 4, and 1 minus 9z when z is greater than negative 4. We want to find the limit as z approaches negative 4 of f of z. So we're going to proceed similar to the previous piecewise function problem. So we want to find the limit as z approaches 4 from the minus side of f of z. And in that case, that'll be taking this piece right here, the 6z piece. So this will be equal to negative 24 because these two pieces are linear functions, so there shouldn't be any discontinuities. And then we also want to take the limit as z approaches 4 from the plus side of f of z. So from the plus side, right? Oh, this will be negative 4, by the way. Sorry. Yeah, it's actually negative 4, not positive 4. My bad. So approaching z approaching negative 4 from the plus side will be taking the second piece, the 1 minus 9z piece. So this will be 1 minus 9 times negative 4, which is equal to 37. So you see negative 24 doesn't equal 37, so the limit does not exist, or we use D and E. So this is the first instance of a limit not existing, and it's because the limit as z approaches negative 4 from the left-hand side doesn't agree with the limit as z approaches negative 4 from the right-hand side. So we've seen an example in problem 7 where we can construct two pieces, right, in a piecewise function where the limit actually doesn't exist. And in fact, if you were to graph this function, right here off the bat, you kind of detect jump discontinuity because you have from, you know, z less than negative 4, this is just going to be a line, right? And then z greater than negative 4, it'll be another line. But the two lines kind of don't touch each other at the point of z equals negative 4. So you've seen jump discontinuity here, and the limit indeed doesn't exist. So this is kind of a cool connection we've made. So let's move on to problem number 8. So problem number 8 is a different type of limit than prior examples we've seen. So let's get through it. We want to evaluate the limit as x approaches infinity of sine squared x over x cubed plus 5. So one tip with infinite limits like this, like where x approaches infinity, is to think about what terms kind of stay significant versus what terms don't really stay significant. And in this case, we can kind of use the quotient property and work on the numerator and the denominator separately, right? So this is going to be equal to the limit as x approaches infinity of sine squared x over the limit as x approaches infinity of x cubed plus 5. So if we look at the numerator, what is going on? This is a function of sine squared x. So if we recall from what sine function is originally, the sine function is essentially an oscillating function, right? It's just a wave, right? And the biggest value that sine can ever reach is positive 1. So if the biggest value sine can ever reach is positive 1, then the biggest value sine squared x can ever reach is 1. But the problem is, when x approaches infinity, right, Sine squared x doesn't really approach a definite value, right? Because it's just going to be a repeated up and down motion, right? It's a repeated wave. So we don't have a definite value for what sine squared x approaches, but we can confirm that sine squared x is at most going to be 1, right? So we can bound it actually. And in the denominator, right, we see here the limit as x approaches infinity of x cubed plus 5, right? What is happening down here, right? We have a cubic function that's kind of, growing to infinity, right? So when we're adding a large number cubed to 5, the 5 kind of becomes very insignificant, right? Adding 5 to a really large number doesn't really do anything. So like this part kind of like vanishes as shown in orange, right? And you have this x cubed that's kind of dominating. So technically this function is really bounded by 1 over x cubed. And when x approaches infinity in 1 over x cubed, right, this whole thing is going to approach 0, right? Because the denominator is growing so large, but the numerator is just staying at most 1. So because of that, the limit as x approaches infinity of sine squared x over x cubed plus 5 really is capped at 0, right? So 0 is going to be what it really approaches. So we can use this argument to kind of convince ourselves, right? Or we can just go off of first intuition. Sine squared x is at most 1, and the denominator is growing so big. So if the numerator is not really growing as fast as the denominator, the denominator is going to dominate, right? And, you know, a number over a really big number is going to get close to 0. And I note that we don't have to worry about sign here, SIGN, because the denominator is growing so fast. So that takes care of problem number 8, and hopefully this builds an intuition of how to solve limits of the form where x approaches infinity or negative infinity. So let's move on to problem number 9. All right, so problem number 9 is one where we have to be a little careful on. We do have to use similar principles that we did on number 8, but let's go through it step by step. So we want to find the limit as x approaches infinity of 5x plus 3 over the square root of 3x squared plus 1. And now the 3x squared plus 1 is all under the square root. So what's happening, right? So when we work on the numerator and the denominator separately, right? So in 5x plus 3, when x gets really large, this 3 becomes very insignificant. And in the denominator, right, when x grows super large, right, adding 1 to a really large number kind of doesn't really do anything. So this is the problem we're trying to solve, right? The limit as x approaches infinity of 5x over the square root of 3x squared. And if we can make an algebraic simplification. This is just 5x over x root 3. And note in this case, since x is approaching positive infinity, right, we can assume that x is going to be a large positive number, right? But at the end of the day, right, the x's here cancel out, and we approach 5 over root 3. Cool. So this takes care of problem number 9 and gives you another example of where infinite limits kind of come in handy. What we observed here is potentially a horizontal asymptote, as discussed in the prior video, building intuition about limits. Okay, now we're on problem 10. So problem 10 is not really taking limits of functions, but we're kind of using properties of limits to solve problems, right? So we know that the limit as x approaches 3 of f of x is 5. The limit as x approaches 3 of g of x is 9. So we want to find the limit as x approaches 3 of the quantity 5 f of x plus 9g of x over 7 plus x cubed. So what do we do here? We can take advantage of 3 properties: the addition property, the constant multiplier property, and the composition property, right? And also the quotient property. So we can simply let h of x equal this 5 f of x plus 9 g of x over 7 plus x, right? Or we can actually do this. Like, let me make this a little bit more formal. So let's let h of z equal z cubed, right? And we can also let g of x, right, equal this 5 f of x plus 9 g of x. Actually, let's make this j of x so that we're not using the same letter. So what we're really doing is we're really taking the limit as x approaches 3 of h of g of x, right? It's a composition. So what can we do? We can kind of bring the limit inside, right? So this limit is equal to the limit as x approaches 3 of 5 f of x plus 9 g of x over 7 plus x all cubed. And now what do we know? We know that the limit as x approaches 3 of f of x is 5, so this is going to be 5 times 5. The limit as x approaches 3 of g of x is 9, so this is going to be 9 times 9. And then we can plug 3 in for x in the denominator, and we're not going to get a division by 0 error. So the answer really becomes 25 plus 81 over 10 cubed. And you can kind of put this in a calculator, but I just want to get to an expression where you can kind of handle the rest. So this is how we solve problem number 10. It's pretty straightforward once you use the limit properties and proceed step by step. Okay, so we've solved problem 10. Next is problem number 11. So problem number 11 says f of x, g of x, and h of x are continuous functions. And we know this information right here. We want to find the limit as x approaches 3 of h of g of f of x. So this problem hints that we should be using the composition property of limits. So this limit right here is equivalent to h of the limit as x approaches 3 of g of f of x, right? But hold on, Karthik. G of f of x is a composition, right? So can we just, take this composition property one notch up? And indeed so, right? So this limit right here is equal to g of limit as x approaches 3 of f of x. Now, what is the limit as x approaches 3 of f of x? Well, that's going to be 5, right? So this is going to be g of 5. What is g of 5? That's going to be 9. But we have the h on the outside, right? So what is h of 9? This is going to be 9 squared plus 3. This is going to be 84. So again, limit properties do save the day, and sometimes they are the unsung hero. And a problem like this kind of really showcases the value. All right, cool. So last problem of today. Here's another interesting limit problem. Now, this type of problem is a limit as x approaches infinity type problem, but you might be surprised here that this doesn't really look like some of the prior problems we've done, right? So one first guess that somebody commonly does is say, oh, x is going to infinity, so x squared and 14x. X squared will kind of dominate, but the 14x kind of really doesn't do anything, and they'll mistakenly get to the point that this limit approaches 0. Now, that intuition is something I can totally understand from learning calculus, but we need to be a little careful, right? And the reason why we have to be a little careful is that, x is approaching infinity, so x is growing big. So x squared and 14x are both growing big. So we can't really just nilly-willy kill out 14x like in this type of scenario. So what can we do? Well, we can employ a clever trick, right? So remember how I said that in the beginning of the video that you can kind of perform any algebraic manipulation you want as long as you don't change the value? Well, we can do that very well right here, right? So this limit, right, is equivalent to taking the limit as x approaches infinity of square root of x squared plus 14x minus x over 1. And wait a second, we have this square root term added or subtracted to some other term. Maybe we can try using the conjugate trick. And indeed, that might be a good shot. So we multiply by the conjugate, right, in both the numerator and the denominator because we don't want to change the value. And what does this give us? Well, in the numerator, right, we get x squared plus 14x minus x squared. Notice that we have the difference of two squares like form right here. In the denominator, we have square root of x squared plus 14x plus x. So we see here that the x squares cross out, right? And now we're left with, I should actually be writing the limits here. We're left with the limit as x approaches infinity of 14x over the square root of x squared plus 14x plus x. All right, so now we have to solve this type of problem where x approaches infinity, right? Sorry, I'm just making this a little nicer. Okay, so we have this limit left to solve, right? So what are we going to do? Well, we can kind of break the problems into two separate problems, right? So the limit as x approaches infinity of 14x, we can't really do anything about that. The 14x kind of dominates, right? Since it's the only term in the numerator. But the denominator, right? What we do notice is this, right? So we notice that in the square root, right? You have this x squared plus 14x term, right? And yes, your intuition was right about, x squared kind of dominating the 14x. So that part we can legally make that conclusion, right? So this 14x term kind of vanishes, right? Because x squared is going to overtake, right? And now what do we have here, right? What we have is the limit as x approaches infinity of 14x over the square root of x squared plus x. And this simplifies to the limit as x approaches infinity of 14x over 2x, which equals 7. So you thought initially that this limit was going to approach 0, but it actually turns out, with a clever algebraic trick with the conjugate, we find that the limit actually approaches 7 when x approaches infinity. So this is a cool problem that I personally want to wrap up on because it's not an intuitive problem at first, and most people make the common mistake that I've mentioned kind of earlier. So thank you very much for watching this video and kind of, going through the practice exercises with me on these limit problems. If you have any questions or catch any mistakes when I went over these problems, please, please, please leave comments in the video. And don't forget to like and subscribe and spread the word to your friends who are wanting to refresh on calculus or learning calculus or currently studying it. And yeah, I'll see you in the next video.